We are going to be solving Cambridge International AS and A Levels Chemistry Paper 1 Multiple Choice October-November 2025, Paper 14. Question number 1 says helium forms an ion He32 plus 1. Three statements about this ion are listed. It contains 2 protons. You should know that this number right here, this lower number, this is the proton number, and this upper number is the neutron number or nucleon number. So the number of protons are going to be 2 and the number of neutrons are going to be 3 minus 2, which is 1, because that's the nucleon number, the mass number. From that you subtract 2 and then you get 1. Three statements about the ion are listed. It contains 2 protons, right? It contains 3 neutrons. No, it contains 1 neutron. It contains 1 electron. So let's see. Helium has 2 electrons initially, helium atom. And plus 1 means it lost 1 electron. So now it only contains 1 electron. It contains 1 electron. That's about the helium ion. Atom contains 2, but ion contains 1. So 1 and 3 are correct. The table shows first 5 ionization energies of element X. Element X is in period 3 of the periodic table. What is element X? So over here, the big task is to figure out the big jump. Big jump means that between 2 ionization energies, where's the big jump? So over here from 700, we're going to 1400. So that's almost double, right? From 1400, we're going to 7700. So that's almost 6 to 7 times. This is 2 times, almost. I'm just assuming almost. From 7,000 to we're going to 10,000. That's not even double. That's like not even double. And from 10 to 13, that's not even double. So the big jump I spotted is between second and the third ionization energies. You can spot it yourself. That's the biggest jump. And then, you know, because this is the big jump, that means the third electron is being removed from an inner shell. That means the valence shell has 2 electrons. That means it's in group number 2, because the last shell has 2 electrons, because the third electron is being removed from an inner shell. Hence, the correct answer is going to be in any element that's going to be in group 2. Sodium is in group 1, magnesium in group 2, silicon in group 4, argon in group 8, or group 0. So it's going to be magnesium, because the highest jump is between second and third ionization energies. Methanethiol, CH3SH, burns is shown. Methanethiol plus 3 oxygens from carbon dioxide, sulfur dioxide, and water. A sample of 10 cm cube of methanethiol gas was reacted with 60 cm cube of oxygen. Look, 1 cm cube reacts with 3 cm cube. That means mole ratio in gas is equal to the volume ratio. That means if you have 10 cm cube of methanethiol gas, it's going to react with 30 cm cube of oxygen, but we have 60. That means 30 cm cube of oxygen is in excess, because only 30 is reacting. Both samples were measured at room conditions. What would be the final volume of the resultant mixture of gases measured at room temperature? Final volume of the resultant mixture of gases at room temperature. We know that the limiting reactant over here is methanethiol. So moles of the limiting reactant determine the mole of the product. So if we have 10 cm cube of this, we're going to form 10 cm cube of carbon dioxide, 10 cm cube of SO2, and water is in, we're dealing with room temperature. And over here they're asking about the mixture of gases. At room temperature, water is not going to be a gas. It's going to be a liquid. So we don't consider water here. So how much gas we have? We have 30 cm cube of oxygen, 10 cm cube of carbon dioxide, and 10 cm cube of SO2. So that makes a total of 30 plus 10 plus 10, 50. A solution containing 4.4 gram of an organic acid is exactly neutralized by 25 cm cube of 2 mole per dm cube of sodium hydroxide. The acid is 1 COH group in each molecule. What is the empirical formula of the acid? First things first, we know that R is the organic part, and COH, the acid part, is going to react with NaOH to form RNA, right? RCOO-Na, to be more precise, RCOO negative Na plus water. Now, first things first, we got to calculate the moles of this thing. So moles equals to concentration, which is 2 times volume, which is 25 upon 1000. This gives me 0.05 moles of my NaOH. Now I know the mole ratio of NaOH and this acid is 1:1. I just made a balanced equation, and that's how I know the acid is also going to be in 0.05 moles. Now I have the mass of the acid and I have the moles of the acid. How do I figure out the MR? MR equals to mass divided by my moles. Mass is 4.4, moles is 0.05. My MR comes out to be 4.4 divided by 0.05. It's 88. Now I know that 88 is my MR, and in my MR there is this thing as well. I want to figure out the R group. So out of my MR I'm going to subtract the COOH part, right? So 88 is my total MR. I'm going to subtract from it the COH part. Carbon is 12, oxygen is 16, oxygen is 16 plus hydrogen is 1. I'm subtracting this part from it. So 88 minus 12 minus 16 minus 16 minus 1, and that gives me 43. And I know that if I have 3 carbons in a row and these many H's, 1 2 3 4 5 6 7, 12 times 3 plus 7, that gives me exactly 43. That means I have 3 carbons, 1 2 3 carbons, and the fourth one carbon is my acid functional group, and that is exactly the molecular formula of my compound X. Now they're asking about the empirical formula. Molecular formula is, this is butanoic acid. So the molecular formula comes out to be C4H8O2, right? And if I convert it into empirical formula to 1 times 2 to 4 times 8 into 2 times 4. So C2H4O. C2H4O. In which said do all molecules have all their atoms arranged in one plane. One plane means that the molecule should be flat, right? It should be in one plane. AlCl3 is a planar molecule. It's trigonal planar. BF3 is a planar molecule. You need to know the geometries, but this is a pyramidal, right? It's a pyramidal molecule. Why? Because the problem is that phosphorus, despite having 3 hydrogens attached to it, why is it still pyramidal? Because it has a lone pair on top, and this lone pair pushes this down. So that's why it basically forms a pyramid down. So it's trigonal pyramidal, so not flat. NH3 again pyramidal. C3H6 is an alkane, and alkanes are tetrahedral. They're not flat. Over here C2H4 alkene. Alkenes are 120 bond angle. They're trigonal planar. CO2, it's a linear molecule like this. So the bond angle is 180 degrees. So it's in one plane. H2O, despite being bent in shape, it's a plane molecule. There's a difference. Bent does not mean you cannot lie on one plane. Something like that's bent can lie on one plane, but something that's tetrahedral cannot lie on one plane. There's a difference. You need to understand this difference. Bent means it's just like this. It's a V. You can place a V on your flat surface, but you can't place a tetrahedral structure that's coming out and going in a flat plane. So D. The diagram shows the bonding in a molecule of propine. Which type of hybridizations are shown by the carbon atoms in propine? So this carbon atom is making 4 single bonds. So that's easy. It's sp3 hybridized. And this carbon atom, it is sp hybridized because number of attached atoms plus lone pairs. It is 2 attached atoms. This carbon has 2 attached atoms. 1 attached atom, this part, and 1 attached atom, this part. So there are 2 attached atoms. So 2 attached atoms plus number of lone pairs. There's 0 lone pairs equals to 2. That means 2 orbitals are involved in mixing, and that are one s and 1 p orbital. This is again sp hybridized. 2 sigma bonds are being formed, sp hybridized. One this or hybridized orbital, one this hybridized orbital. These 2 bonds are formed by unhybridized orbital because these 2 bonds are pi bonds. Pi bonds formed because of unhybridized. So this or sp hybridized, and this is sp3 hybridized. So we have sp and sp3. sp2 nahi hai, sp and sp3 only. The boiling point of water is higher than that of hydrogen sulfide, which statement explains the difference in the boiling points. So we know that water is this, and because of these lone pairs, there is a hydrogen bonding between the partial positive hydrogen and this lone pair. That's why. So the bond energy of OH is greater than the bond energy of SH. Bond energy has nothing to do with boiling points. When you boil something, you don't break the bonds. That's the thing. You just break the intermolecular force. The intermolecular forces in H2 are weaker, they're stronger because it has higher melting point. The SH bond you don't care about the bond is longer. No. The significant intermolecular hydrogen bonding in water, yeah. Hydrogen bonding plays a part. And how do hydrogen bonding occur? If you have nitrogen, fluorine, and oxygen bonded to a hydrogen, direct bonding between them. Which would describe silicon dioxide. Electrical conductivity, it's obviously going to be a non-conductor. SiO2 is a giant covalent structure. Solubility, insoluble. The data are needed for the question, what is delta H for this reaction? So we have formation data for all three things. So we're going to just draw a Hess cycle. This P4O10, the formation is -3012, 6 H2O formation, 6 times -286, and then 4 times H3PO4, -1279. Okay. Now, how many delta H, where does the delta H come? Delta H comes over here. This is the delta H. Now, how many cycles can we make? One cycle, this, and one cycle, this. And now we have to equate the two cycles. In the first cycle, the pink one, this delta H is coming, this is coming, and this is coming. And in the second cycle, that's yellow one, only this thing is coming. So now we have to equate the two. So -3012 plus 6 times -286 plus delta H naught R equals to 4 times -1279. And now, if we're going to solve for delta H naught R, let's see what we get. We take the things on the other side, so it becomes 4 times -1279. And then it becomes plus 6 times 286. And then it's plus 3012. Plug it in your calculator, see what you get. I get -388 kilojoules per mole. This comes out to be my answer. In an experiment to measure the enthalpy change of neutralization of hydrochloric acid, 20 cm³ of solution containing 0.4 mole of HCl is placed in a plastic cup of negligible heat capacity. Okay. This amount of HCl, this many moles of HCl, a 20 cm³ sample of sodium hydroxide. Now we're going to do a neutralization reaction, measure the heat change. 0.4 mole of NaH, same initial temperature, added to flask, temperature rises by 15 Kelvin. If the heat capacity per unit volume of the final solution is this, what is the enthalpy change of neutralization? Okay, first we got to calculate the formula. Q equals to mc delta T. M is the mass. What's going to be the mass? 1 cm³ equals to 1 gram. Over here we have 20 plus 20, that's 40 cm³. So we're going to have 40 grams. Times C, C is equals to 4.2 times delta T. Delta T is 15 Kelvin divided by the moles of the limiting reactant. Limiting reactant out of HCl and NaOH both are in equal amounts. And if you make the equation, they react in equal amounts. So you can take any one. So divided by 0.04. Which statement matches? Or draw on bow. This option C matches. You can see it for yourself. Acidified potassium manganate react with iron, ethanoate, DOA, ions, whatever the reaction taking place as shown. How many moles of iron, ethanoate, D8 will react with 1 mole of potassium manganate? Okay. So over here, when this MnO4 thing is reacting, it's basically gaining 5 electrons. And when this iron, ethanoate, D8 thing is reacting, it's losing 1 electron and then 2 electrons because this is a combined thing. This is combined. Look it for yourself. So we're losing 3 electrons and we're gaining 5 electrons. The problem is that a loss and gain of electrons should be equal. So if 1 mole of MnO4 is losing basically gaining 5 electrons, then we need 5 electrons to be lost as well, right? So if 1 mole is losing 3 electrons, we need 5 electrons. How many moles are we going to have? 5e equals to 3ex. 5e upon 3e equals to x. 5 divided by 3. What do we get? We get 1.67. That's the moles of FeC2O4 that are going to generate 5 electrons. Because 1 mole, look at my ratio, 1 mole generates 3 electrons. How many? 3. 1 plus 2, 3. 1 mole generating 3 electrons. So 5 electrons are going to be generated by x moles. X moles of Fe2C2O4. That comes out to be 1.67. How do I know I need 5 electrons? Because 5 electrons are being gained. So obviously 5 needs to be lost. So with 1 mole of potassium manganate, I need 1.67 moles of this thing to lose 5 electrons so it can gain 5 electrons. Nitrogen dioxide decomposes on heating according to the equation. So 2 moles of nitrogen dioxide forming 2 moles of nitrogen monoxide plus oxygen, when 4 mole of nitrogen dioxide were put into a 1 dm cube container and heated to a constant temperature. The equilibrium mixture contains 0.8 mole of oxygen. What is the value of the equilibrium constant Kc? Okay, so what's happening over here is that we have nitrogen dioxide that's forming 2 moles of this, forming 2 moles of NO plus O2. When 4 mole of nitrogen dioxide were put, so initially we put 4 mole of this, we had 0 mole of this, 0 mole of this. Okay, nitrogen would put into a 1 dm cube container and heated. The equilibrium mixture, so these were the initial, that's going to be the change, and then we have the equilibrium mole. So we draw a table like this. Equilibrium moles of oxygen are 0.8. Now the ratio between oxygen, that means 0.8 moles of oxygen are obviously formed. Okay, that's unarguable because initially we had no moles of oxygen. Now look at the ratio between oxygen and nitrogen dioxide. It's 1:2. So that means double moles of nitrogen dioxide and nitrogen dioxide are going to be utilized. So if 0.8 moles of oxygen are formed, 1.6 moles of nitrogen dioxide are utilized, right? And the ratio between nitrogen dioxide and nitrogen monoxide is the same. So 1.6 moles of nitrogen monoxide are going to be formed. Over here it's 4 minus 1.6. That is 2.4. So that's the equilibrium thing. Now we put our products on the top and the reactants below. So 1.6 squared, because there's a 2 here, multiplied by 0.8 upon 2.4 squared. I guess that's the answer, right? 1 particle of X reacts with 1 particle of Y in a single step reaction to produce 2 particles of Z. 1 particle of X reacts with 1 particle of Y to form 2 particles of Z. The reaction is exothermic, so we have a delta H which is negative and reversible. Reversible means it goes both forward and backwards. 3 statements about the forward and reverse reactions are listed. Which statements are correct? The activation energy for the forward reaction is equal to the activation energy of the reverse reaction. Not at all. Look, I am going to show you something. That's the energy table you draw, right? This is an exothermic. So if I say these are my reactants, these are going to be my products, right? And over here, since this is an exothermic reaction, endothermic, sorry. That's for endothermic. I just need to change the positions. This is exothermic, right? Now it's exothermic. For an exothermic reaction, the activation energy is this. And for endothermic reaction, the activation energy is going to be for the same reaction. If it goes reverse, it's going to be this. So for exo, it's only this part. For endo, it's this part. So for endo, the activation energy is much more than that for exo. Got it? So option 1 is straight away wrong. At equilibrium, the frequency of collisions between 1 particle of X and 1 particle of Y is equal to the frequency of collision between two particles of Z. Frequency. You know what equilibrium means? A rate of forward equals to a rate of backward. And you know what? Rate depends on does not depend on the frequency of collision, depends on the frequency of effective collisions. Right? Not on the frequency of collision, frequency of effective collisions. There might be more collisions happening between X and Y compared to two particles of Z. But what is effective, what's producing the product matters. So this doesn't matter. I'm again telling you, rate is not dependent on frequency, it's dependent on the frequency of effective collisions. It might happen that frequency might increase, but unless the effective collisions don't increase, your rate don't increase. Get it? At equilibrium, the frequency of effective collision between one particle of X and one particle of Y is equal to the frequency of effective collision between two particles of Z. That's correct, because effective collisions is what matters. Next question states that when two aqueous solutions are mixed, the reaction between them is very slow. An effective catalyst is added to the mixture without any change in temperature. Which statement about the catalyst is correct? It increases the average energy, decreases the activation energy. It changes the distribution of energies. No change to the Boltzmann curve. Just the activation energy moves backward. It allows greater number of reactant particles to react per unit time. That's correct. It's gonna make greater number of particles to react by decreasing the activation energy. Doesn't does anything to the particles, just allows greater to react. It increases the number of reactant particles with the most probable energy. No, that's going to affect the shape of the curve. It doesn't affect the number of particles. Just allows them to react by, generating an alternative pathway for the reaction to proceed. A mixture of gases reacts faster as its temperature increases, which will explain this. The activation energy remains unchanged. True. Temperature doesn't affect the activation energy, only catalyst does. More particles have energy equal to or above activation energy. That's correct. That's why, because what's your temperature is going to do to the Boltzmann distribution curve? If this is your curve, temperature is going to move the curve something like this. And when it does this, what happens now, the particles with the most probable energy increase, with greater than activation energy increases. So temperature increases the number of particles greater than activation energy, and catalyst changes the activation energy. More particles have energy equal to or above the activation energy. True, that's how the reaction is going to get faster. True, true, false. This increases the rate of successful collisions. Yeah, true. When successful collision increase, the activation energy remains unchanged. Yeah, true. The activation energy remains unchanged. True, not false. Why am I saying false? I just said that, yeah, it doesn't change because temperature cannot, so it's B. True. A student investigated the chloride of a period 3 element. This is what the student wrote down as the observations. A compound was white crystalline solid. It dissolved easily to give a solution of pH 12. There's no chloride in period 3 that gives pH 12 in water. Sodium chloride is going to give pH 7. MgCl2 is going to give pH 6.5. Then all the rest pH, Al2Cl6, pH 3. And then you have SiCl4 and PCl5, pH 2. No, pH is 12. That's wrong. So at least one of the recorded observation is not correct. The which graph shows the relative melting points of elements magnesium, aluminum, silicon plotted against their relative electronegativities. We know as we move across the period, electronegativity is going to increase. So phosphorus is going to be most electronegative and magnesium is going to be least. Phosphorus most, magnesium least. So done. Now comparing the melting points, we know that silicon is going to have the highest. So silicon should be at the top of the melting point. Yeah. Option number B. Okay. Cesium and barium are in period 6. That means they have 6 shells, which was correct. The larger ionic radius. So cesium and barium. So for that, you got to consult the periodic table. That is the periodic table. So here we have cesium, here we have barium. We know that across the period, what happens to ionic radius? What happens to ionic radius? Does it increase or decrease? It's going to decrease because the nuclear charge is increasing. So nuclear charge is increasing. It has 56 protons while it has 55 protons, whereas the electrons are going to be same once they form ions. So greater cesium is going to have. Greater ionic radii is going to be of cesium. The higher melting point, obviously of barium, because across the period, you know, group 2 is going to have a higher melting point because, you know, there's stronger bonding, stronger metallic bonding in group 2 compared to group 1 because they lose 2 electrons, and, you know, 2 delocalized electrons attracted towards a 2 positive charge compared to 1 electron attracted towards a 1 positive charge. So C. Magnesium nitrate, MgNO32, will decompose when heated to give a white solid. We know what is it going to form? MgNO32 is going to decompose to form MgO plus half O2 plus 2 NO2. Okay. A mixture of gases, one of the gases released oxygen. 29.7 gram of anhydrous magnesium nitrate is heated until no further reaction. What is the mass of the oxygen produced? So if you have 29.7 gram of this, how many moles do we have? This is the mass divided by the MR. So what's the MR of magnesium nitrate? 24.3 for magnesium plus 14 plus 14 plus 16 times 6. I don't know if I'm going to get it right or not. 148.3. 29.7 divided by 148.3, that is 0.2 moles. If I have 0.2 moles of magnesium nitrate, I have half moles of oxygens, right? Because look at the ratio. It's 1 ratio half. So if I have 0.2, I get 0.1 mole. And the mass of 0.1 mole of, what is the mass of the oxygen produced, is going to be 0.1 mole of oxygen. So mass equals to moles times MR. What do I get? 3.2. 3.2 moles is 0.1. MR is 32. Multiply them, you get the mass, which is 3.2. I hope you got it. This was easy question. Okay, which shows the trends in the named properties going down group 2 nitrates. Thermal stability definitely increases. Why? Bonding gets stronger. Volume of the gas produced measured room temperature when 1 gram of anhydrous solid nitrate is thermally decomposed. As you go group down, for 1 gram, the moles are going to decrease. Why? Because look, moles equals to mass over MR. Now you're taking 1 gram, so mass is constant. If you know even a little bit of physics, if you keep this thing constant, as the MR is going to increase, the moles is going to decrease. So as we go down group, MR increases, so moles decreases. When moles decreases, volume of the gas produced is also going to decrease. Do you understand what happened? MR increased going down group, so moles decreased. When moles decrease for the same mass, because mass is 1 gram, that means mass is constant. So volume of gas is going to decrease because now you have less moles. So option number B. X, Y, and Z are 3 aqueous solution. Equal volume of pairs of the solution are mixed in observation noted. X mixed with Y shows no reaction. Okay. X plus Y equals to no reaction. X mixed with Z shows an immediate reaction. X plus Z equals to some reaction. Okay, Z mixed with Y shows no reaction. Z plus Y equals to no reaction. What are X, Y, and Z? So X mixed with Y shows no reaction. So if X and Y are mixed, is there going to be any reaction? Bromine and iodine, they're simple compounds. Why would they react? No, chlorine and iodine, they don't react. Ions react. So X mixed with Y shows no reaction. X and Y, HCl and HI. Let's see. Okay, they're not going to react. HCl and Beer2, right? They're not going to react either because Beer2 is a stronger oxidizing agent than chlorine. Okay, X mixed with Z shows an immediate reaction. So X mixed with Z is going to show a reaction. HCl and Beer2 are going to show a reaction. Over here, HCl and Beer2 don't show a reaction. Right? X mixed with Y shows no reaction. Okay, so we're looking for no reaction. I'm so sorry. We're looking for no reaction. So no reaction was over here, reaction happened. So we cross option D. Oh, in these three reactions do not happen. Okay, now X mixed with Z shows an immediate reaction. So X and Z is going to show a reaction. Br2 and HBr, they don't show a reaction. So option A cross. Cl2 and HBr show a reaction. So option B tick. HCl and Br2 is going to show a reaction, right? No, they're not going to show a reaction because Br2 cannot displace HCl. So option B, the correct one. Br2 cannot displace HCl, but Cl2 can displace HBr. Bromide from the HBr, whatever. An excess of chlorine gas is bubbled into hot potassium hydroxide solution. Which chlorine containing species are present? If it's hot, then we're going to form this thing and NaCl. NaCl and NaClO3. Right? NaCl and NaClO3. ClO negative we form when it's cold sodium hydroxide. So that's the correct answer. The oxides of nitrogen, NO and NO2 act as pollutants in the Earth's atmosphere in a number of different ways. 3 statements about the oxides of nitrogen are listed. They react with oxygen and water vapor. They react with oxygen and water vapor to form nitric acid, a constituent of acid rain. Yeah, that's correct. They do form acid rain. Next, they react with carbon monoxide to produce, no, not with carbon monoxide, with unburnt hydrocarbons. They catalyze the oxidation of sulfur dioxide in the formation of sulfuric acid and they catalyze the formation of sulfur dioxide to sulfur trioxide, and then that sulfur trioxide forms sulfuric acid. So 1 and 3 are correct. Which reagent when mixed with ammonium sulfate and heated liberates ammonia? Anything with an ammonium salt that's basic is going to produce ammonia. So aqueous bromine, no. HCl, no. Calcium hydroxide, yes, because it's basic. Any base plus ammonium salt gives ammonia plus salt plus water. Okay, 2 hydrocarbons, this and this, react separately with chlorine in the presence of UV light. In each reaction, free radical substitution occur. Which was correct? Identity of the hydrocarbon that can also undergo electrophilic addition. So we're looking for a hydrocarbon that is going to have double bond. So if we draw it, CH3, first I'm drawing this, then we have a carbon with a hydrogen, then we have a carbon with a CH3, and then we have a carbon with a CH3. So there's a double bond here. So the first one can also undergo electrophilic addition because of this double bond. So the first one, this and this. A termination stage of the free radical substitution of the saturated hydrocarbon. This one saturated because the first one we just figured out has a double bond. Double bond means unsaturation. So this is going to be the reaction. 2 free radicals. Wait. No. Which one's saturated? Which one's unsaturated? 2 free radicals are going to react, and this one's the saturated one, right? This one matches this. Have to be careful. And then this free radical. So we're going to go with option number E over here. I hope you understood that what was the procedure. First we figured out the saturation and unsaturation, and then we just realized that the unsaturated one can undergo electrophilic addition because you can add an electrophile to it, because the alkene bond, it's a nucleophile. So electrophile can be added to it. And then saturation means no double bond. Okay, the structure of compound alpha anion is shown. The alpha anion, how many stereoisms exist with this molecular form? Stereoisomers we're finding. I can see this is a chiral carbon. The second thing I can see, this bond feels like it can show cis trans, because this group attached to one side, hydrogen attached to one side, hydrogen attached to one side, and this group attached to the other side. So we have 2 stereocenters. 2 raised to power n. 2 raised to power 2 equals to 4. Do we have any options that says 4? Yeah. So 4. Simple. 2 stereocenters. 2 raised to power the number of stereocenters, and we subtract -1 from our answer if it's a symmetrical alkene, but it's unsymmetrical. Structure and stereoisomers should be considered when answering this question. A mixture of 1-chlorobutane and 2-chlorobutane are heated with an excess of NaOH. How many different organic molecules will be produced? 1-chlorobutane, that means 1, 2, 3, 4. Then there's a chlorine here. So if we add ethanolic NaOH, what's going to happen? Elimination, chlorine eliminated, double bond formed here. And then if I have 2-chloroethane, a double bond can either form on the first carbon, or a double bond can either form on this carbon, because with this chlorine there are 2 beta carbons and hydrogen is removed from the beta carbon. So either from this beta carbon or from this beta carbon. So this and this are the same structures. So I just realized something. We were right. We're going to form butanene and then we're going to form butene. But you know what's the twist here? I'm not adding hydrogen. You guys are not in O-levels IGCSE that you need hydrogens everywhere. You can understand from double bond what I mean. There's going to be cis-butene and trans-butene. Because look, on one side it has a CH3 attached, on the other side it has a hydrogen, then it has a CH3 and then hydrogen. Like, I know, I personally know that this cis-trans thing is the worst. That's why we're going to have 3, not 2. The diagram shows the skeletal formula of the hormone testosterone. That's the hormone that makes you angry. What is the molecular formula of testosterone? Okay, so now we need to calculate the carbons and hydrogens and everything. So carbon, 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 carbon. Now we gotta add the hydrogens, right? 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 3, 1, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 1, 2, 1, 2, 3, यहाँ पे 4, यहाँ पे 1, यहाँ पे 1, 2, 3, 4, यहाँ पे 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Are we done? Are we done or not? Is there any more carbon whose valency is not filled? Yeah, this. No, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, now we calculate the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Oh my god. There's no option that says 29. So we gotta calculate it again and again. Okay? So we are missing something. What are we missing? 1, 2, 3, 4. 1, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. I've added either one extra hydrogen, I've missed one. Look, at this carbon I added one extra. So it's a total of 28 in O2. Right? Done. Pinenes are unsaturated compounds. The structure of 2 pinenes are shown. A mixture of these 2 pinenes react with hot concentrated acidified KMnO4. What are the molecular formula of the organic products? Break this bond, and then we have this carbon that's gonna double bond OH. Then we have this carbon. This is gonna form a ketone because that's a that has two R groups attached to it, and this only has one R group. When you have one R group, you form a carboxylic acid. When you have two R groups, you unarguably form a ketone. Over here, you break it from here. This is gonna form carbon dioxide, and this one has two R groups attached to it. Look here. It's gonna form a ketone, so C double bond O. So now what is the molecular formula of the organic products? Okay, so we have two organic products. One organic product is this whatever, because it's gonna break from middle, and one organic product is this thing. Now we gotta calculate the number of atoms. That's the worst thing you can give a child to do, like in the exam, counting. But still, we're forced to do this. One, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. C10. Time for oxygens. 1, 2, 3 oxygens. C10O3. C10O3. This cut. C10, I already know it's H16. I don't need to count H now. So that's the good thing. I know this. Now I just need to count the number of hydrogen. I already know there are 9 carbons. So that's the benefit of shortlisting. Now I only need to calculate the hydrogen in beta, pinene, whatever. Okay. Calculating hydrogens here. Okay, 1, 2, 1. If I just start counting them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, H14. H14 or H16. H14, this comes out to be my correct option. An organic ion containing a carbon atom with a negative charge is called a carbanion. Okay. An organic ion containing a carbon atom with a positive charge is called a carbocation. The reaction between NaOH and 1-bromobutane proceeds by SN2 mechanism. What is the first mechanism in this step? Between NaOH and 1-bromobutane proceeds by SN2 mechanism. Attack by a nucleophile on a carbon atom with a partial positive charge. That's correct. Heterolytic bond fission, homolytic bond fission happens in SN1 mechanism. And that's a heterolytic bond fission in which the bromine takes the electrons from carbon. So it's option number A, because we're dealing with SN2 mechanism in which there is an attack. 2-chloropropane, 2-bromopropane reacts separately with the aqueous NaOH, which shows comparison of the rate. Bromo is going to react fast because carbon-bromine bond is weaker than carbon-chlorine bond. So it's going to break more quickly. Explanation. The first ionization energy, the CBr bond is weaker. Yeah, that's correct. The diagram shows the structure of compound X. X undergoes hydrolysis to form product Y. X undergoes hydrolysis to form product Y, in which all of the bromine atoms are replaced by hydroxyl groups. So all of the bromine atoms are going to be replaced by OH. What are we adding to it? Can you guess? What are we doing? All bromine atoms, we're replacing bromine, we're adding aqueous NaOH. Product Z is formed by the oxidation of Y. Okay, so now what do? We remove all bromines. So bromine, tata bye-bye. And now we add, in place of bromine, OH. OH here, OH here, OH here. And now product Z, that's product Z, is formed by the oxidation of Y. X undergoes hydrolysis to form product Y. This is product Y, in which all the bromine atoms are replaced. Product Z forms from the oxidation of Y. Now if you oxidize it, what's going to happen? This right here, this carbon right here has one carbon, two carbon, and is one hydrogen. That's a secondary alcohol. Secondary alcohol oxidized to form a ketone. This is a secondary alcohol. This is secondary. This is secondary. So Y is a secondary alcohol. Yeah, and Z is a ketone. Yeah, because when we're oxidizing it, this is Y. And when we're going to oxidize it, all the OH groups are going to be oxidized to form a ketone. So, step 1 converts the OH to something, and then step 2, you add 2 OH to it. Is it reduction? If we reduce, can we reduce alcohols? I don't think. We can dehydrate them. First we dehydrate them, right? First we dehydrate, we're going to form a double bond here. And once we form double bond here, we add acidified cold KMNO4, and then we're going to get a diol. So it's oxidation, and the oxidizing agent is not K2Cr2O7, remember. K2Cr2O7 cannot oxidize alkenes. So it's going to be that, what do you call that thing? KMNO4. Orange PPT with 2,4-DNPH, definitely aldehyde or ketone. Tolerance reagent, no change, definitely not an aldehyde. Alkaline I2, yellow PPT. Okay, so this is an aldehyde, right? Cross. This is an aldehyde. You can see it for yourself. C double bond O, and then there must be an H, so cross. So this and this. Now, alkaline I2 gives a yellow PPT. Over here, you can see there's a CH3 over here. So this group can give you yellow PPT. So it's option number B. And this also group can give you yellow PPT. Because for yellow PPT, what do you need? You just need a CH3 C double bonded O. That's how you get yellow PPT in ketone. So that's the option. Over here, you're not going to get yellow PPT because there's a CH2 here. There's a CH2 here. What do we need? We need a CH3. Okay, butanol, this is butanol, and HCN are mixed with a little KCN, react together in nucleophilic addition reaction. Butanol, this is butanol, and HCN mixed with a little KCN, okay, that's the catalyst, react together in a nucleophilic addition reaction. We know nucleophile is going to be added. Which description of the mechanism of this nucleophilic addition is correct? The pi bond pair of the C double bond O accepts H plus from HCN and then CN negative attacks. No, first CN negative attacks. The pi bond pair from CN negative attacks the partial positive carbon, and HCN then donates H plus 2. The pi bond pair from CN negative. Not the pi bond pair, the lone pair from CN negative. The lone pair on O accepts H plus from HCN, yes, and then CN negative, no, first CN negative attacks. That's how my concepts are clear. I don't know the marking scheme. I promise I don't know. I'm just doing it by my concepts. A lone pair from CN negative attacks the partial positive carbon, correct, then O negative accepts H plus from HCN. That's the mechanism. When you know mechanisms, you know what's going to be the answer, what happens first. The structural formula of compound P is shown. Okay, we're dealing with an ester, I think. Let's draw each. Which pair of compounds would react to produce P? P can be formed by reacting two other organic compounds in the presence of a suitable catalyst. Okay, let's see what ester are we dealing with. That's ethyl propanoate. So ethanol and propanoic acid. The structures of 3 organic compounds are shown. The structures of 3 organic compounds are shown. Which compounds produce ethanoic acid when heated with HCl? Ethanoic acid when heated with HCl. Look, nitriles undergo acidic hydrolysis and esters also undergo acidic hydrolysis. So not an aldehyde, definitely. Nitrile, yes, undergo acidic hydrolysis. And this is an ester. So it's going to break from here and this part is going to form the ethanoic acid. So it's 2 and 3. I wish it comes out to be 2 and 3. Yeah, option D. Okay. When bromoethane C2H5Br is heated with NaOH and ethanol, what's going to happen? In ethanol, elimination reaction is going to take place. Easy peasy lemon squeezy. PMMA is a rigid polymer. The repeat unit is shown. Which monomer is used to make PMMA? Put this bond inside. So I have a carbon that's attached to a CH3. CH3. This is going to be a CH3 unit when an H is going to come here. No. CH2, because there's a double bond here. So a double bond here is CH2. I need a CH2 on one side, CH2, a C on the other side, and then I need a CH3 on one side, CH2 on one side, and then I need a C double bond O D. See it for yourself. You just have to open this thing. It's coming out to be D. Put in the double bonds, like put in the extension bond inside and make a double bond. Okay, a sample of helium contains only 2 isotopes every 10 atoms in the sample. There are 6 that have 38 neutrons and 4 that have 40 neutrons. Okay. 10. Total abundance. 38 times 6 plus 40 times 4. What is the relative atomic mass? Just solve this and you're going to get it. 38 times 6 plus 40 times 4 upon 10. 38.8. 38. We're talking about neutrons. 38.8. That's going to be the neutron number, and then you add the proton number to it. I don't know the proton number, but I know proton can only be a whole number. So when I add a whole number to this number, I'm going to get this. Easy. Hope you got it. This was the neutron number I got. And now I know when I add the proton number to it, proton number cannot be in decimals. So obviously this is going to be the only decimal I can get when I add a whole number to it. So that's option B. I hope you got it. Bye-bye.